analyze your network data using the network package in R. And the network package allows you to do some pretty powerful stuff with the visualizations. So I'll walk you through how to take your matrix, and we left off here with the matrix, and put it into the network package, which now that we've done that careful work to set up our matrix should be fairly straightforward. So I'm going to go ahead and load the network package, then run the edge_network command on our matrix and plot it. So what we have here is our matrix with the nodes colored blue, our edges colored gray, which we set here using the edge color command and vertex color command, and the vertex cell expansion command to get the nodes a little bit bigger, just so we can see them. So, and if we look a bit closer, we've created an object of class network. So this actually has attributes, 10 vertices, and it's a directed network. The hypergraph and other stuff we don't really need to go into today to create these visualizations. So if we look at our network, or our vertex attributes, what we have are two attributes. One of them is helpfully named NA, and the others are vertex names. And if we look at NA, it's actually just a list of true and false values telling us where the edges are. So it's not very useful, or where the vertices are. And so the vertex names, though, are useful because those map onto our original node labels. So we can see here. So if we return to our original test plot, we actually, let's say we have data called sector. We can take the sector variable and turn it to color and plot them onto our nodes using vertex attributes. So here I've created a vector of length 10, which has color names, and it's length 10 because that's the same length as our node or vertex labels. So if we set that using the set vertex attribute command here, we're going to set it with the attribute name node color so we can access it later under that name. And the value will be that node color variable I just created, which is essentially random for this demonstration, but in any other case it would actually represent some kind of data that you would want to represent, like sector. And V is our vertex IDs, and this is a little bit different than our vertex names, because our vertex ID is actually just a sequential list of numbers which represents the vertices. So we have to be careful here. So V actually represents our vertex IDs, and we can do that by setting basically telling R to generate a sequence of numbers the same length as our network size, or our N. And that's the default option. I just wanted to show you what was kind of going on under the hood there. So again, these are our vertex names, and these are our vertex IDs. So now that we've set the vertex attribute, we can access it using in the plot command and set it using the vertex color option or argument here. And then we access using the get vertex attribute command and our attribute name, which is node color. So when we plot it, now the nodes are a different color corresponding to what I've set earlier, which is useful, but you're also going to want to access the edge list to modify the edge values, and you can do a lot of powerful things with this once you start to get under the hood and play with it. So again, our edge values are just true and false, telling us where the edges are located, but to really get in there and modify that edge list, we want to take the actual whole edge list apart and look at it. So as we see here, the edge list has two dimensions, rows and columns. So we have 2 columns here and 72 rows. This is what it looks like just as raw data. So you can see actually when we look at it, there aren't as many edges as we would expect if every cell in the matrix were represented in the edge list, because we have a 10 by 10 matrix. What this is showing is that the edge list only contains values that are not missing, so and not 0. So we need to kind of be mindful of that and take the edge list structure on its own when we modify the edge list attributes. So we can take each row of the edge list and take those row and column values, and what we get is the value in the matrix that corresponds to those rows and columns. So this function just takes a matrix and an edge list and does just that, and gets the edge values that map directly onto the edge list from the matrix and tags their names. So you can see we have name 1, 2, 3, and each of the values. So that way, when we go to check our object using indexing, it's going to map onto an object that has the same length as our actual edge list. So to do that, I create a new object called eColor, which is just the color gray repeated over the length of those edge values we created just now. Now I check the edge values directly and modify eColor depending on which one of those E values is greater than or equal to 4. So remember, which returns index values, so that's what I'm using here when I'm modifying. This command just returns the index values I need to modify. So now, just like we did earlier for vertices, we set the edge attribute with a new attribute called edge color, and we use the eColor values from earlier. And because we went ahead and tagged the edge names in, I went ahead and specified E here as just the names of E values. So now that we've set the edge attribute, we can access it using an edge color argument, using the get edge attribute command. And so we specify the edge list here as the part of, this is the element of net called MEL, which is not very helpful, but it basically corresponds to the edge list, and our attribute name of edge color now. So we can see what that looks like is that only edges that meet that specified criteria, which is this case 4 or higher, are highlighted. So you can use this to highlight various elements in the matrix and map those onto your graph and actually do even cooler stuff. So in this case, what we have is edge color just for those values that are 4 or higher. But what if you want to highlight some other more complex element in your network, like reciprocal edges? So let's say you want to identify those nodes which kind of regard each other highly. I wrote this little function here, so we set a reciprocal cutoff value of 3 or higher, and basically check each element of the edge list and get its reciprocal value. Check the reciprocal value, and if they're both greater than or equal to the reciprocal cutoff, then our function returns true. So we'll see that what that looks like here is just another object called hrecip that is a vector of true-false values or Boolean values that tell us whether or not a tie is reciprocal. And like before, I wanted to create this with a length of 72, which is in this case the length of our edge list. So, and do the same thing, create that vector of colors that's just gray, and then check hrecip using the which command that creates an index that we're going to use to color reciprocal ties as green. Then we use the set edge attribute command again to set a new attribute called isReciprocal with the value of our reciprocal color vector. And again, I went ahead and tagged the edge names as the names of the hrecip variable I created just for convenience here. So plotting that again gives us highlighted nodes, this time only ties that are reciprocal above that certain value. So this is a primer on how to access your vertices and your edges in the network package. And this basically gives you a lot of leverage depending on how much extra data you've collected and how many questions you have to create different plots that may be informative in different ways. So it all depends on kind of what's of interest to your viewer. But once you have these tools mastered, you can kind of go in and select exactly what you want to view and how to highlight it to best represent the data you're trying to represent.